by Ekaterina Rapinchuk. She's an assistant professor in math and computational mathematics, science and engineering at the Michigan State University. And her talk is entitled Applications of Auction Dynamics to Data Defined on Networks. So Ekaterina, at this point, you should be able to share your screen if you want. So thank you, Ekaterina, for joining. And thank you again, everyone, for joining the conversation. Remember that you can ask questions in the chat. Thanks.
Hello, I was wondering if everybody can see my slides.
Yes.
And it can hear me. Okay, perfect. Okay, so first of all, I'd like to thank the organizers. I would like to thank the organizers very much for allowing me to give a talk today. It is a pleasure to give a talk at this conference. So today I'll be talking about applications of auction dynamics to data defined on networks. And part of this work is joint with Matt Jacobs at UCLA and Sunny Masadoglu at University of Michigan. So the problem that we'll be considering today is the following. So it is to segment a data set into a pre-specified number of clusters. So we'll label the number of clusters by M, and we're going to use a small amount of labeled data. Now, if you look at the data set on this slide, it's a data set of images of different animals. So our problem here would be to assign the correct animal to each image. Animal label to each image. So this problem is found in many applications. It's a very important problem, and some of the applications are listed on the bottom of the slide. So the goal of this talk would be to introduce a new forward and reverse auction method for data classification. And a very interesting feature of this method is that it proceeds in a similar way as a real-life auction. So before I go into details about the method, I would like to just briefly mention some of its advantages. So perhaps the most important advantage is that we found that it requires less training and label data than other methods we compared to reach good accuracy. And this is very important because it's relatively easy to find unlabeled data, but finding labeled data is very expensive and can take a long time. So that's a very important advantage. So the other two I want to mention as well, the first one is the fact that our method, we can incorporate class size constraints. So if you maybe know the lower bound and the upper bound of the size of each class, you can input that into the method to reach perhaps a higher accuracy. And this method is also unconditionally stable. So with respect to parameters, so we will always converge to a partition of the data having the right class size properties. Okay, so the framework we'll be using is a graphical framework. So we're going to embed each data set into a graphical structure with vertices and edges. So the vertices will represent the elements of the data. And then between some vertices, there will be edges. And on each edge, there will be some weight assigned on it, which describes the degree of similarity between the two nodes is connecting. So if the weight is large, then the two vertices are similar, and if the weight is small, the two vertices are not similar. So just very briefly, since computing the weight function is a very important part of the graphical framework, the way we compute the weight function is by first computing something called a feature vector. So we assign each data element a d-dimensional feature vector, which somehow describes the data. And we are going to use this feature vector to compute the weight function. Now, there are many ways to compute the weight function, but a general idea is that you want to construct the weight function so that it assigns a big value for similar elements and a small value for dissimilar elements. And an example of a weight construction that one can use is just a Gaussian. So a Gaussian measure that uses the two feature vectors. Okay, so our model is going to incorporate a couple of things. So first of all, it's going to incorporate label data. So any data elements with known class. We're also going to incorporate class size information. So we're going to restrict the size of class I to be between two values. So lower bound L sub I and an upper bound U sub I. And if you don't know any class size information, then what you can do is you can just set the lower bound to 0 and the upper bound to the size of the data set. And our method is also going to incorporate region homogeneity terms, which measure how well data elements fit into particular classes. So a little bit about the region homogeneity terms. So they, as mentioned before, they measure how well elements fit into classes, and using them can improve accuracy compared to models that are just based on terms with weights, so just based on edge terms. And the goal would be to formulate the region homogeneity terms so that R sub I of X is small if X is likely to belong to class I, and large otherwise. And so the application that I'm going to talk about in this talk will be to 3D point clouds. And for this application, we're going to construct the terms using things like the correlation matrix, normal vectors, and variation of normal vectors. So before I go into the technical details, I just want to briefly talk about the notation. So soon we're going to formulate an optimization problem over a function U. So the function U is going to go from the vertex set to the simplex. And in some sense, so U sub I of X will represent the probability that an element X belongs to class I. U sub X, so U of X is going to be a probability distribution. Okay, and then you have a couple of other variables. So let's denote L sub X to be the label of any data element with known class, such as the training data. And E sub I, let that be an indicator vector with 1 in the ith place and 0 elsewhere. And let's denote T sub S and T sub R by unlabeled and labeled data, respectively. So our goal is to assign a label to all elements in TS, so the unlabeled data. Okay, so we're going to consider the following optimization problem with two kinds of terms. So the optimization problem is over the function U. And U is constrained to be positive. And the energy function that we're going to optimize over, or the energy function that we're optimizing, is composed of two types of terms. So the first term is an edge-based term, so it's going to include the weight function. And so the first term is a relaxation of the graph cut. And the graph cut attempts to find a partition of the data so that the sum of the weights between elements belonging to different classes is as small as possible. And this is a convex, this is a relaxation of the graph cut. So this is an edge-based term. And the second term is a region-based term, which has the region homogeneity term. And of course, you have the constraints. So you have the constraint that U must be a probability function, and then you have the class size constraints, saying that the size of each class must be between the lower and an upper bound. And you also have the constraint of the label data. So the function U of X, if X is a labeled element, is constant. So we're going to set that to be the indicator vector of the label. And then, so once the optimizer of U is found, then you can obtain a partition of the data so that by the following scheme. So we're just gonna assign each element to the class that gives the largest value in U of X, or its probability distribution over the classes. And then we can obtain the partition of the data in the following way. Okay, so an interesting property is the following. So interesting property is the following. So for a positive semi-definite weight matrix W, we get that the energy is actually a concave function of U. And therefore, what we can do is we can consider the following scheme, which successfully minimizes linearization of the energy we were considering in the previous slide, subject to different kinds of constraints. So yeah, so we're gonna successfully minimize linearizations of the energy subject to constraints. And then at every iteration, you can obtain a partition of the data using the procedure we just talked about. And due to the concave property, we see that the energy will be non-decreasing at each step. And so every iteration of our scheme will produce a partition of the data. Okay, so our approach to solving the optimization problems in our scheme will be to connect each problem of our iteration in the scheme to a modified version of the assignment problem. And we'll solve this modified version using forward and reverse auction dynamics. Okay, so I'll just briefly mention what the assignment problem is about. So the assignment problem is a very important combinatorial optimization problem. So it involves two sets of equal size. And there's a weight associated to each pair of elements where the first element is in the first set and the second element is in the second set. And the goal of the assignment problem is to find a one-to-one matching from the elements of the first set to the elements of the second set, so that the total value of the total sum of the weights is as large as possible. So we're going to connect solving each problem of each iteration to solving a modified version of this problem. So let's just rewrite the usual assignment problem in an optimization notation. So using binary, so indicator vectors, we can write each assignment problem as an optimization problem. So we're optimizing over a binary vector Z. We're optimizing some linear combination of elements of Z under some equality constraints. And I would like to note that if you relax the binary constraint on Z by allowing each value to take a value in between 0 and 1, what actually happens is the solution to the problem will not change. Okay, so what we'll do is so what happens is that each step of our scheme is actually equivalent to a modified assignment problem, where you're optimizing over some linear combination of elements of U, and there's some certain coefficient in front of each U term. And you have equality and inequality constraints this time. And after finding the optimizer, you can obtain a partition of the data by a simple thresholding operation. So we'll denote the coefficients in front of U by A sub I of X. So these will be called the coefficients of the assignment problem or the auction coefficients. And just intuitively speaking, the auction coefficients or the coefficients of the assignment problem will represent, so the coefficient A sub I of X will represent how much X, the data element X, wants to be a member of class I. Okay, so each modified assignment problem of every iteration, we're going to solve using a modified auction dynamics technique. And this technique will be equipped with something called a market mechanism with the following components. So what we're going to do is we're going to equip each class with a changing price. So if an element X wants to be a member of class I, then they must pay some price. Now, if classes are popular, what we can do is make their prices more expensive. So maybe some elements will switch their choice to another class. Now also recall that each class the size of each class must fulfill a lower bound. And if a class sort of has trouble getting a lower bound amount of members, they can offer an incentive, a changing incentive to attract elements. And we're going to assume that data elements would want to be would want to be members of classes that offer the best value to them. So in particular, they would want to be members of classes that maximize the following expression. So A sub I of X, meaning how much they want to be a member of that class, minus the price plus the incentive. So whichever class maximizes this expression, that would be the class that offers the best value to them. And note that if the price is increased, then this expression will be lowered. Now, what we can do is we can assign each element to a class that offers the best value to them. Now, we can do that, but class size constraints will probably not be satisfied if we do this. Now, an interesting question is, does there exist a certain price vector and a certain incentive vector, so that if we do this for those values, if we assign X to a class using the strategy, then that would result in a feasible matching, or a matching that satisfies class size constraints? And the answer is yes. So there do exist certain price and incentive vectors, so that if classes are assigned according to the strategy, we have a feasible matching. So the next question is, how do we find these values? And the answer is we turn to the dual of the modified assignment problem. So if we consider the dual of the modified assignment problem, then the equilibrium price and incentive vectors will actually be the solution to the dual assignment problem. So the auction dynamics we'll use will simultaneously compute the equilibrium price and incentive vector, and then we'll assign the data elements to classes using these values. Okay, so as I mentioned before, we propose to solve each step of our scheme using forward and reverse auction dynamics with a market mechanism. And each step of our scheme will consider a different assignment problem that has different auction coefficients. So every iteration will consider a different assignment problem with different coefficients, and each iteration will produce a partition of the data set into a certain number of classes. And the partitions will get better and better in some sense. And as I mentioned before, our method will simulate a real-life auction. Okay, so each step of the forward and reverse auction dynamics will either modify the prices or the incentives, or increase the number of elements matched to a class. So this is similar to an auction where you either increase the price of the item or you sell the item. So you match the item to a person. So our auction dynamics will be divided into two steps. So a forward auction and a reverse auction. So in the forward auction, the elements will bid on the classes. So this is similar to just a real life auction. So that the data elements will bid on the classes. Now the reverse auction, which is the second step, in this reverse auction, sort of the reverse will happen. So now the classes will the classes that haven't yet achieved the lower bound amount of members will compete for the elements by providing incentives to attract that lower bound amount of members. Okay, so in the forward auction, what will happen is the following. So if a data element is unmatched to a class so far, then what they will do is they will bid on a class offering the best value to them. So they'll bid to the class, and they'll bid a certain value, which has an epsilon parameter, which exists so that the auction dynamics doesn't stall, so that it terminates. So a data element can bid to a low demand class or a high demand class. So a low demand class doesn't yet have the upper bound amount of members. And if this is the case, if it bids to a low demand class, then it gets accepted immediately. Now, if it bids to a high demand class, which is a class that already has the upper bound amount of members, so it can't have any more members, what will happen is that the lowest bidder of the class so far will get kicked out, so it'll get unmatched. And then that data element X will get into the class. Now, because this is such a popular class, the price of the class will then get increased. So what will eventually happen is the prices of the high demand classes will cause, so the prices of the high demand classes will rise so much that they'll cause unmatched elements to switch their bid to another class that might offer a bigger bang for their buck. So the upper bounds on the classes fit very nicely in this perspective, but we need the lower bound, we need a reverse auction to fulfill the lower bounds on the classes, on the size of the classes. So this is just a pseudocode for the forward auction. Now for the reverse auction, the procedures is the following. Okay, so if a certain class doesn't yet have the lower bound amount of members, then what is done is you find an element matched to another class that was the closest to choosing the deficient class. And it is done by a certain computation. And then once that element is found, you transfer that element to the deficient class, update the prices and incentives if necessary. And if the class still doesn't have the required number of members, then you repeat this procedure until that class has the required number of members. And if the class is full, you just proceed with the next deficient class until none of the classes are deficient. And this is the pseudocode for the reverse auction. Okay, so the overall algorithm is the following. Recall that our scheme involves solving a series of assignment problems, and each iteration will produce a partition of the data. So what we do is we, for each iteration, we recompute the auction coefficients, and then we do something called an epsilon scaling for efficiency. So we're going to alternate between the forward and reverse auction while decreasing the epsilon parameter each time. And the epsilon parameter was found in the bid value of the bid value that each element bids during the forward auction. And once the epsilon is small enough, we then output the current partition and then proceed with the next iteration. So this is the pseudocode for the overall algorithm. Okay, so I don't have too much time, so I'll try to be fast here. So the one application we applied our algorithm to is classification of 3D point clouds, which is a very important problem in mapping and navigation. So point clouds arise through laser-based imaging and usually represent 3D objects and scenes. So a laser will scan an area, and then the goal would be to classify the scene into some objects. Now, this problem is very challenging due to many different reasons, such as lack of adequate high-quality training data. So we applied this method to 3 different kinds of point clouds. So, and all of them had at least 1 million points. For the label data, we used a very small amount of the overall data. So for one data set, we used less than 0.5%. And then for the other 2, we used 2.5% of the points as labeled. And our method took, so it's very efficient. It took at most 2 minutes for this data, including the graph. And the reason why it takes so little to compute the graph is because the feature vector is very small. So for the first data set, the point cloud only had three points per element. Okay, so for the first data, this is just some results. So the first data set is just a point cloud of some scenes from CMU campus. And we divided the data into classes such as road, building, and vegetation. Some more scenes from the data set. So in one of the scenes, we used 4 classes. So here, for the last scene, we also had a pole class, so a utility pole class. And then some data for the other 2 data sets. So we have the Ankeny data set divided into 4 classes, so road, ground, building, and vegetation, and also the buildings data set. And we divide into building, vegetation, ground, and road. So maybe just very briefly, so we introduced a modified action dynamics technique for data classification, and perhaps the most important advantage of the method is that it requires perhaps more less training data than the methods we compared to. So thank you very much.
Great. Thank you, Ekaterina, for the presentation. So let's open the floor for questions. So remember, if you have any question, you can write it in the chat. We have a few minutes for those. So let me just kick this up with, so what happens if we do not know upper and lower bounds on the classes and we just set them to 0 and n respectively? Like, would the auctions just end after the first step, or what would happen there?
Oh, no, so let me just go back to this slide. Yeah, so if you don't know any class size information, then you just set the lower bound to 0 and the upper bound to the size of the data. And then, I mean, that doesn't really affect, so the auction dynamics, it will just proceed more based on the auction coefficients. Right.
So there will not be like any reverse auction, right? Because no one would be below 0. Is that correct, my intuition?
That's correct. So exactly. So the auction dynamics will just be based on the auction coefficients. That's right. Correct. Okay.
Any other questions for the speaker? Yeah, so here we have one by Francesco. Thanks. Sure. I was wondering how sensible it is in terms of the number of classes you know. I mean, does things get much better when you have more known labels?
Oh yeah, so as with probably most data sets, the more label data you have, the better it'll perform. Was that the question?
Yes. Or yeah, well, apart from that direction, do you have any other kind of way of quantifying this, maybe with experiments that you run or something, or not really?
Oh wow, let's see. So we did find that you don't need too much training data. At some point, the accuracy will sort of increase very slowly. So we found that you don't need much training data, and at some point the accuracy won't increase much as you increase the label data, the amount of label data.
Perfect. Okay, so we are right on time. So there you go. So Francesco seems to be satisfied. So we are right on time. So thank you, Ekaterina, again for the presentation and for joining us today.
Thank you.
Thanks a lot.